Today I'm going to try and help you understand why the absorption band for a carbonyl vibration depends on the functional group. If we jump straight in, we can see that the carbonyl group, C double bond O, turns up in a number of different functional groups, from acyl chloride to aldehyde to ketone to amide. However, the amount of energy it takes to make this bond vibrate more strongly clearly depends on the nature of the group that is bonded to the carbon of that carbonyl group. Makes a huge difference, 200 centimeters to -1 difference. Now, it's not about electronegativity per se, because we can see here that at one end of the scale we've got chlorine, and at the other end of the scale we've got nitrogen, and both chlorine and nitrogen have very similar electronegativities. This is actually about whether these R groups, i.e. the ones bonded to the carbon atom of the carbonyl group, are electron donating or electron withdrawing. And this is basically a balance between the inductive and conjugative effects of these groups. What we know is that when we have electron withdrawing, let's see if I can write that in neatly enough to be able to read, electron withdrawing R groups, such as chlorine, then this increases the wave number. If we're increasing the wave number, we are increasing the energy or frequency of the radiation absorbed in order to make our carbonyl bond vibrate more strongly. And at the opposite end of the scale, we have electron donating groups. So electron donating R group. And they decrease the wave number, i.e. we require less energy, a lower frequency of radiation to make this carbonyl bond vibrate more strongly. I'm going to start with electron donating R groups. Now these R groups are able to donate electron density towards the carbon of a carbonyl group, either through inductive or conjugative effects. And we're going to start with inductive. Let's have a look at butanone. So this is an example of a ketone, and the carbon in the carbonyl group is bonded to two alkyl groups. Remember that the carbon is delta positive and the oxygen is delta negative in this carbonyl bond, because oxygen is considerably more electronegative than carbon. Now we know that alkyl groups are able to donate electrons, or electrons are attracted towards the delta positive carbon of the carbonyl bond. As a result, this lowers the polarity of the bond, and the result is that this carbonyl bond is a little longer, a little weaker, and vibrates at a lower wave number. So let's summarize that. We are lower the polarity because electrons are being pushed towards the delta positive carbon, which means that the carbonyl bond is a little longer or weaker, and so it vibrates at a lower wave number. The second way that R groups might be electron donating is through a conjugative effect, and an amide is a good example of this. So if we take carbonyl, we can bond it to a hydrogen and an NH2 group. Remember that the carbon is delta positive, the oxygen is delta negative. Now nitrogen has a lone pair of electrons, and this lone pair of electrons exist in a 2p orbital, which means that they're readily able to delocalize to form a pi bond with the 2p orbitals of carbon. And we can show that with a curly arrow. So, lone pair of electrons moves, and this pushes the pi electrons onto the oxygen atom of the carbonyl group. The result is a resonant form of this amide, which I can draw like so. So we've now got a single bond to the oxygen with a negative charge. We've got our hydrogen. We've got a double bond to the nitrogen. This nitrogen's lost its lone pair of electrons, so it's now positively charged. But the key thing here is that what I have is a single carbon bond oxygen, which is longer and weaker than the carbonyl bond, so it's going to vibrate at a lower wave number. Now, a more interesting question is, why does nitrogen not behave like chlorine? It is more electronegative than carbon. Why is it not pulling the electrons away from the delta positive carbon? Well, it is. Everything in chemistry, or many things in chemistry, are actually a balance. So nitrogen is more electronegative than the carbon. It is capable of attracting electron density from the carbon atom, but this negative inductive effect is far weaker than the electron donating conjugative effect that we've outlined here. We see a similar conjugative effect when comparing the carbonyl stretch for saturated and unsaturated molecules. So if we go back to propanone, so that is a saturated ketone. We have got the carbonyl stretch at around 1715 centimeters to the -1. But if we were to compare it with cyclohex-2-enone, what is that, you ask? Well, if I can draw a hexagon, which is often not the case, it looks like so. So we've got the carbonyl group up there, and it's unsaturated because we've got a double bond. We've got the alkene functional group there. This too can exist as two resonance forms, in that we can have electrons from the double bond move, and from that bond move onto the oxygen, and the result is this resonant form. And once again, as we will see, this resonant form has got a single bond to the oxygen, and single bonds are a little longer, a little weaker than double bonds, and as a result, they're going to vibrate at a lower wave number. The wave number for this one actually turns out to be 1680. So it's a fairly significant effect that we're seeing here. So we've explained the effect of electron donating R groups on the carbonyl vibration. What about electron withdrawing groups? Well, let's go back to our acyl chloride. We know that chlorine is significantly more electronegative than carbon, and it pulls electrons away from that delta positive carbon. As a result, this is going to increase the polarity of the carbonyl bond, which means as a result this carbonyl bond is a little shorter and stronger, and so it's going to take more energy to cause it to vibrate more strongly. More energy, higher frequency, so vibrates at a higher wave number. Why doesn't chlorine donate a lone pair of electrons to form a conjugative electron donating effect like nitrogen does in the amide? If we think about chlorine, it has 3 lone pairs of electrons. However, these lone pairs are situated in the 3p orbitals. If you remember, for nitrogen, lone pair was in the 2p orbitals. And there is a very poor overlap between the 3p orbitals of chlorine and the 2p orbitals of carbon. So result, formation of a carbon-chlorine pi bond is not favourable. It doesn't happen. No conjugative effect possible. If you're interested in exploring this in a little more detail, I've got videos for valence and molecular orbital theory somewhere on the site. I'll pop an end card round about here so you can click on it if that's the way you want to go. There's also, if you scroll down in the blurb, a link to the Crunch Chemistry website where you can find exam questions with fully explained answers. And these answers focus on foolproof methods for calculations, especially the tricky ones, exam technique and wording. If that's something that would be useful to you, then head over to Crunch Chemistry and let's see what we can do to help. Now, if this has been useful to you, then please think about liking the video and hit the subscribe button. It makes a huge difference to a small channel like us. I look forward to seeing you next time.